Hello there, Year 10. This is Mr. Stevens with your lesson for today. We are going to go over some of the answers for the myimaths homework to solidify your understanding and maybe give you a few little tips and tricks. So, we're dealing with differentiating polynomials. When you differentiate polynomials, you are probably familiar with this gradient function here on the right. This tells us the gradient at any point on the function itself. Let's start with the first one. The first one is y equals 8. I'm going to use a graphical method to solve this one. When y equals 8, we have a horizontal line at, of course, y equals 8. The gradient function will give us the gradient at any point on this line. What is the gradient of this line? You guessed it, the gradient is 0. No matter where I go on x, I'm always going to get a gradient of 0. So when we differentiate a constant, we always end up with the same answer, 0. And here it is. The gradient for any constant y equals 8 will always be 0, regardless of where you are on the line. For the next one, y equals 7x. Let's look at this one and also have a graphical answer. You may recall from graphing lines y equals mx plus c that lines have a constant gradient. It's always the coefficient in front of x. In this case, what's the coefficient of x? That's right, 7. So the gradient function will be equal to 7. Because regardless of where you are on this line, what value of x you are at, you'll always get a gradient of 7. The gradient for any line, y equals ax, will always be the number in front of x. The third one, y equals 3x to the power of 3. Let's look at this one. So, for this one, we have a function that is always changing. It's always changing the gradient. If you were to sub in x equals 0.5, you would have a specific gradient. But if you move along the curve and find the gradient at x equals 1, for example, you'd have a much larger gradient that's changing all the time. To solve this one, we simply use the gradient function. It's remarkable how simple this is, considering it's so powerful. If n equals 3 in our case, we bring down the 3 and multiply. And then we reduce the exponent by 1. So 3 minus 1 is 2. So in our case, the gradient function is 9x squared. If I sub in the value of negative 0.5 into this function, it will generate the gradient at that point, which is remarkable. So, we use the gradient formula for higher powers of x squared, cubed, to the power of 4, etc. The next one I'd like to look at is this one, y equals x plus 6 all squared. For this one, there's a preliminary step that must be done. We can't differentiate it in this form. We have to expand first. To expand this, we end up with x squared plus 12x plus 36. Once we're in this format, we have 3 separate terms, all involving powers of x. Then, and only then, can we differentiate the function. We do it as normal. For the first one, x equals 2x to the power of 2 minus 1. We bring down the exponent and multiply, and then reduce the exponent by 1. For the next one, y equals 12x, just like before, it's the constant term in front. When we differentiate it, it always has a gradient of 12. Then we simplify, and we end up with 2x plus 12. And the final one I'd like to look at y equals 4 over x to the power of 4. Again, we need to rearrange this first before we can differentiate. And here it is. It's only possible to differentiate when the x is in the numerator, when the function is in line in the numerator. So, recall that for exponents, 1 over x to the power of n from previous classes, when you move it to the numerator, the exponent changes sign. So we end up with x to the power of minus n. Now, differentiate as normal. We bring the exponent down and multiply. Minus 4 times 4 is minus 16. And then we take away 1 from the exponent. We are taking away 1 from minus 4. We're going lower. So minus 4 minus 1 is minus 5. And that is the final result. This function will give you the gradient at any point in x on this curve right here. Okay? Now, if you'd like, you can pause the video and try the other ones that I did not show you. Okay, welcome back. Here are all the answers. Thank you very much, and see you tomorrow.